Hi guys, this is the autocoder again, and I just show another example. Show a closed loop system with a PID controller and Unity set point. Let the P, I and D terms be variable from slider controls. Auto scale the y-axis. So this is like a little academic exercise to show people, to show students how PID control would work. Animation. Let's run that and see. It's running on QN3 coder, 30 billion parameters. As I said in the previous video, it's only running 4 billion at a time. I say only, but that's why it can run on my graphics machine, on my graphics card. And so off it goes. Sending to the model, and here it's got past mistakes it's been made in similar. It wasn't for this example, but I think it was Kalman filters I was working on. It's just some warnings about it's going to do things with matrix multiplication, which it won't be in this case because it's more MATLAB library type thing. It's not running MATLAB, but it's running the Python version of MATLAB library, which is very similar in many ways. Oh, here we go. So there's the program it's come up with. I don't know what that is, how long that is. It's not that big. And here we've got output of a system. Let's turn everything down. It should be going up to 1 because the set point's 1. So let's increase the gain. And that's just proportional gain. So it's gone to about 0.8 something, not 0.9. So it's at the steady state error you can see here, as you'd expect just from proportional gain. So what we can do, I normally don't have the gain that high, turn it down a bit and introduce some integral action, and that should get rid of the offset. And you can see it integrating away the error, and the more integral action I put in, you see the error goes down to 0. It's beautiful, actually, beautiful simulation. And now we're left with all this overshoot. And just to show if I got integral action on its own, what happens is that I end up with oscillations. Well, it just completely oscillates. And I've had previous videos illustrating this for real systems. This is, of course, a simulation. So this is back. Now, to get rid of the overshoot, what we can do is increase the proportional gain. Sorry, the derivative gain, derivative action. You see the overshoot coming down. There it goes. Oh, down, 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 down. Okay. And then, oh, well, you might be happy, but it depends on the overshoot that you want. And these are opposites of one another, integral and derivative. I can put more integral in, but you see you get more overshoot. As I turn down the integral, I get this offset, but it's highly damped, but I get a huge offset, so it's no good without integral. Just about every control system needs integral, unless there are some exceptions. If you maybe got a heating controller or something, you don't really need integration because it doesn't matter if there's an offset by a tiny amount. For very high precision you would, of course. So there's our error gone down to 0, more or less, overshoot. And I can make it faster by increasing the proportional gain, so I get a faster rise time, or I would, in the frequency domain we'd say it's a faster bandwidth. You see the time taken is less now as I increase the gain, so it's getting there faster, but I've introduced overshoot, so I'd need more derivative action to get rid of that, but I've run out of derivative action, so I could turn down the integral action a bit. I'll actually turn down both of them. There is a limit in a real system. I actually haven't put it in this one, so this is very idealized. In real systems we've always got something that limits the bandwidth, as I think I've mentioned before. I'll maybe do that one next to